be to look at some example problems that I've got here. But first of all, just one little thing I skipped over in the notes up to now. So just look at it on page 3 here. And this just to mention there's a couple of different types of notation that are used for these partial derivatives, okay? So far we've been making use of this variation on the ddx notation, this ddx and ddy, for instance, to represent these partial derivatives. Now, when you're carrying out partial derivatives, when you're dealing with functions of more than one variable, you should always use that, different form of the letter D there for that. It's convention, it's what everybody does in mathematics, and it's an easy indicator to the reader that this is something different to derivatives of functions of a single variable. Okay, so it's pretty universal practice to do that. It looks quite odd and a bit, like bad spelling if you write normal Roman ddx when it's a function of several variables that you're working on. Okay. But there is, just as in when you were dealing with functions of a single variable, remember we also had this superscript notation, the superscript notation for referring to the various single derivatives. Well, in a similar kind of way, we use a subscript notation illustrated here, f sub x or f sub y, to refer to the x partial derivative or the y partial derivative of a function f. Okay, so those are just two different types of notation, and you'll see both used, and from time to time we'll make use of both. There are kind of advantages and disadvantages to using each. The advantage of this subscript notation is it's quicker to write. You just need the function name and a quick subscript indicating the variable that you've taken the derivative with respect to. So it's less work than writing all that, and it's kind of easier to write evaluation. So f sub x at ab stands for the partial derivative evaluated at ab, whereas using the other notation, you kind of have to say df dx, maybe then evaluated at ab, or else you say df dx in a straight line and say ab down here. It's a bit more awkward. So that's the advantage of the subscript notation. But then the advantage of this other notation is it kind of emphasizes that ddx is kind of like an object on its own. It's a differential operator which acts on the function. And having it written, ddx acting on f, you think of the f as the function sitting here, and you hit it with the operator ddx, and that produces some new function. But the advantage is, here that you can separate out the parts of the notation that refer to the operator and the function f, the thing that gets operated on. Whereas with the other notation, with the f sub f notation, it's not so easy to separate out and say that, well, the subscript is a kind of thing that operates on the function. Yeah, it doesn't really work. So the other notation has that advantage. Okay, but you just need to be aware of them both and recognize what they mean. The other thing, so following on from the last calculation we did an hour ago, which was the tangent plane example 1. So first of all, you need to correct the version in the notes. There's a misprint in the notes at line 1.33, equation 1.33. So we wrote down the correct version earlier. This partial derivative should be 2xy plus 1. This dz dx is 2xy plus 1, and then make the necessary corrections thereafter. But we did it on the paper, and I'll put the scan of those pages up, but you should have that in your own notes. So that should be 2xy plus 1, and then make the resulting changes. And then this, in the break then, I just plotted this quickly. So this illustrates the conclusions from that example that we worked out. So there's two-dimensional subspaces shown here. The curved one is this curved sheet running here. That's the surface defined by this function here, which is the function x squared y plus 2y squared plus x plus 1. That's the function that was in that example. And then this straight plane is the tangent plane. That's the tangent plane defined by this equation here, 13x plus 16y minus 41. So I plotted those using the EZ mesh command in MATLAB. Okay, if you just look up the help on that, you'll see how to use that. Put a description of the function in quotes, and this 0415 is the x minimum, x maximum, y minimum, y maximum of the plots, and so on. Stick those two plots together, and of course, when you do it on the computer, you can use the rotate tool to rotate the whole thing around and view it from different angles and tilt it and whatnot. And you can pretty much convince yourself that, remember, this problem was centered on x equals 2 and y equals 3. So if you look at that base point, which is it that there, is it? Yep. No. So the equation of the tangent plane was z equals 13x plus 16y minus 41. The minus 41 was the constant term appearing in the equation of the tangent plane. Yeah. So this is the point on the floor, and up here is this point P, which lies on both the surface and the tangent plane. And when you rotate the thing around and look at it from different angles, you can get be quite convinced that the plane is indeed tangent to the surface at that point. Okay, it just touches the surface at that point, and the rate of change in any direction along the plane is equal to the rate of change along the surface at that point P. Okie doke. So EZ mesh command for drawing these nice 3D surfaces. Then the main business this evening is to get some practice, a set of problems. So here's a collection of extra problems over and above the ones that are in the exercises and the notes. Perhaps leave those more for the tutorials and so on. But I thought we'd get started and get working through some of these. So the first couple of questions there are, you're presented with some differential equations, and you're given the solutions to them, but just asked to verify that the provided functions are indeed solutions. In the first one, you've got Laplace's differential equation, which is the sum of the two second-order derivatives of a function phi, d2 phi dx squared, and d2 phi dy squared. But the sum of those is equal to 0, and that one possible solution of that is this function e to the x times sine y. So you could verify that. And this other equation here, this time with the function psi, that is. No, yeah, psi. PSI, the Greek letter psi. So this is a function of three variables, x, y, and t. So it's e to the minus t times sine of x plus cosine y. Again, verify that that's a solution of that partial differential equation. So you can work out the derivatives mentioned there and demonstrate that the two sides of the equation hold. In question 3, you're going to look for locations where the two first-order partial derivatives of that given function there are equal to 0, simultaneously equal to 0. And we'll show a graphical interpretation of that. And that kind of looks forward to some of the work we're going to do with stationary points, minimums and maximums of these functions. There's a question 4 on implicit partial differentiation. I haven't told you what implicit partial differentiation is, but you know what implicit differentiation is from your work in first year. So you should be able to adapt that to that. So you get started on these, and in a few minutes, do talk about them and compare your answers with them and discuss them with your neighbors. And I'll discuss some of them on the board in a moment. If you got any questions, please feel free to ask me. Okay, so I'll give you a few minutes to get through the first couple, say, verifying that those given functions are solutions to those equations. Maybe question 3 as well, identifying the simultaneous zeros of the two partial derivatives. That's stealing university electricity. This is witnessing you guys throwing all these balls there. Let's see. The second order x derivative, of course, is e to the x sine y again. Second order y derivative, leave the e to the x alone, it's just a constant multiplying that. You got minus e to the x sine y. And you add those two together. They do indeed give 0. queries so far or anything? So it's just a bit efficient here. When you differentiate psi with respect to t, you're just differentiating the e to the minus t part, you're leaving the rest as a constant, multiplying that exponential. And of course, you just get minus e to the minus t. So you just get minus psi in total, minus the original function. It's a bit quicker to write that down. What would be the second derivative with respect to t? d2 psi dt squared. Just the psi would just be the original function again. Because you get a second minus sign and the two would cancel out. Which functions? Yeah, where did it go? So the reason you're not seeing it is, remember the principle. You're differentiating with respect to x. So any of the other variables, namely y and t, you treat as if they're constant. So where did the cos y go? Yeah, well, that's still my point. If you're differentiating with respect to x, the other variables y and t are treated as just constants. So you got constant here and a constant out the front here. So it just disappears to zero when you, yeah, treat it the same as if it was a plus 2. Yeah. And that same thing explains why the sine x has gone in the middle one. E to the minus t remains there because it was multiplying the sine x. You keep the constants that multiply the function of x when you're differentiating with respect to x. Sorry, the x. Yeah. Thank you. Yeah. Question? So we're adding those two together, and you do indeed get minus psi, which equals d psi dt. Let's move on to questions 3 and 4. Question 2 and 2. So the two, when you work out those partial derivatives, they're both functions of x and y. So I'm looking when I say find all the, so find all the, each point in the plane is an x y. Make them to zero. Find out what the simultaneous solutions are. Yeah. Describe. I'm gonna take this sheet away, yeah? We're all finished with this? Yeah. Yeah. Sorry? Yeah. Well, just describe them in some kind of a. Yeah, well, so they have to both be equal to zero. They're not the only possibilities. Try and describe them succinctly, though. Try and, because we're talking about any point x, y in the plane. So try and get a nice description. So you're on the road to it. Or something else. Try and pin that down and give it a nice description in terms of the plane. Okay? You're thinking about it. So that's what you were heading towards. Actually, I guess this is covered now. So actually, we don't need that when x, y equals 0. I guess we don't need that because that's contained within this. So k is equal to 0. Actually, I shouldn't have said for any. I can simplify this condition here. Yeah, because I shouldn't consider any negative k's here because x squared plus y squared is always going to be a positive quantity. So actually, this is only for any k, for any integer k greater than or equal to 0, any positive, non-negative integer. Yeah, you get z plus. You could write that as well. But which points in the plane are these? Just how would you describe them geometrically? If you looked at all these points x, y, yeah. So yeah, so that's it there, talking about circles. So for this function, the two partial derivatives were there, minus 2x sine sum of squares. df dy was minus 2y times the sine of the sum of squares. That's using the chain rule to differentiate each time. So you've got a function of an inner function of the variable. So you're using the chain rule. We're looking for the simultaneous zero, where these are zero simultaneously. I wrote down first, yeah, because you can see a simple solution when both x and y are both zero. That clearly makes both expressions zero because of this x and y here. But actually, when you think about it a bit more, the other possibilities are to do when this argument of the sign makes the sign zero. So when is a sign zero? When is sign of something zero? Only when the argument is some integer multiple of pi. So I first wrote down whenever x squared plus y squared is an integer multiple of pi. But then I noticed kind of, and you pointed out as well, that actually, well, you don't have to consider the negative multiples because x squared plus y squared is always a positive. It's always a non-negative quantity. So you're adding two squares. So we only need to consider the positive, the non-negative integer multiples of pi. This would include having 0 on the right here. So that would be the x equals y equals 0. So, i.e., to get a more geometric description of it, we were saying there, when x, y is on a circle of radius, see, x squared plus y squared, whenever you see x squared plus y squared, you just immediately think of square of the radius. It should just be automatic in your minds. X squared plus y squared is the square of the radius. So these are circles of radius square root k pi for some integer k greater than or equal to 0. So whenever x and y are such a point, so that one is root pi, the circle of radius root pi. And then there'll be another one, which is radius root 2 pi, and so on. Good circles. So those are the points where the two partial derivatives vanish of this function. Now that has a very strong relationship to the geometry of the surface defined by the function, and we'll be discussing that in detail in a few weeks, but I could at least persuade you of it here. Oops. I was trying to get the tangent plane to work there, but it didn't. So what do I want to do? I just want to plot the surface of this function, see what it looks like. So I'll define gxy, cosine of x squared plus y squared. And then just want to plot 3D cosine of xy. We need to give it an x range. So 30, 30. Just make R be the extent of our plot. We'll start off with R equals 30. Saying x and y is not variables, so we need to do the G. This thing's called G. I think I made it too big. Let's bring it down a bit. Okay. Bring it down a bit more. Okay, so you can start to get, so I wasn't getting a good view of the surface, so I was zoomed out too much before. We can see that this is some kind of an undulating surface, because the height, remember, is just given by this cosine parameter. And a cosine, remember, just varies between -1 and 1. So the height of your surface, the height of parts of the surface is just going to vary between -1 and 1. And it goes like the square of the radius. So as you move out from the origin is in the middle there, x equals 0, y equals 0. As you move out on any line away from the origin, the square of the radius is increasing quite fast. So you're running through the periods of cosine quite fast. So cosine will just be varying between -1 and 1. Okay. So you can see there that at the origin, it's kind of at the top of the hill. But the first circle at the square root of pi corresponds to this first circle here, which is a circle of minimum points of the surface. You can look at it from below there. Below, it's just this first circle here, which is the circular valley bottom, if you like. That's the first circle that we've plotted on our graph there. That's the root pi circle. The next circle out will be this circle, which is at the top of this ridge here, if you like. So after you're from the top of the hill at the origin, you go down into the valley, and then you rise up to the top of this hill. And there's a perfect circle of kind of circular ridge there around the origin. Okay, and then you fall down to the next circle. Okay? So those circles, the circular ridges and circular valleys there on the surface plot are exactly these circles where the partial derivatives are vanishing that we worked out there. In fact, because the way the square root operation works, they'll be packing closer together as you go out. Okay, but we'll be getting on to discuss stationary points, these maximums and minimums of surfaces, and the other types you can have saddle points. We'll be getting on to discuss those in detail in the coming lectures. Okay, so let's have a go at question 4, say, this implicit differentiation question. So the idea for this one is to consider z as a function of x and y. But we don't have a formula for the definition of it. We just have a relationship that's implicitly defined by this equation here. X times y plus y times z plus z times x equals 1. So this relationship always holds for x and y. Yeah. Implicitly defined as opposed to explicit. If you said explicitly defined, you'd expect z of xy equals some function just of x and y. But when you've got this implicit relationship here, this is the function z defined implicitly. Although we can't quite easily, well, let's go ahead and use implicit differentiation. Well, yeah, I just noticed that, yeah, that I didn't give you one that I gave you one that could be just, you can just obtain, so this is, what is it? It's minus xy over x plus y. Isn't that it? So you could just take that as a definition. But then that means we've got two ways to work out the partial derivatives. And we could just, it's good exercise just to demonstrate that the two give the same value. From the one hand, if you want to work with the expression on the right, you're going to have to use the quotient rule, because you've got quotient of two functions of x or two functions of y. So you have to use the quotient rule for differentiating that. But an alternative approach would be to stick with the implicit definition and differentiate this. So our task first is going to be to find dz dx. So the approach here is just to differentiate both sides by taking ddx of both sides. Now we could use this approach as well in places where you wouldn't be able to rearrange the things so conveniently. So, well, the right-hand side is kind of easier because the right-hand side is just a constant 1, so it has a derivative of 0. Then the left-hand side, well, x times y, the derivative with respect to x is just y. So we're thinking of x and y as being the independent variables, and z has dependence on both of them. So when we see y times z, the derivative of that with respect to x will be y times dz dx. But then when we see z times x, we see two factors, z and the x, and they both have dependence on x. So we need to use the product rule. So that would be, you hold the first one the same, you differentiate the second one, so that just gives you back z, and then you have x dz dx. Okay, but now you see we can get an expression here for dz dx by just saying that this is y plus z plus x plus y into dz dx, and that this is equal to 0. So dz dx will just be minus y minus z divided by x plus y. Now we've still got the value of z mentioned in its own derivative. That's okay. It's just saying that the rate of change of z is related to whatever its current value is. Okay. Then you could take a very similar approach to finding the derivative with respect to y. Indeed, because x and y appear symmetrically here, you can probably just make a stab at writing it down straight away. dz dy would just be the symmetric thing, minus x minus z over x plus y. So I can make that jump because the way x and y appear up here is completely symmetrical. Each one is playing exactly the same role as the other. They multiply each other, and they each multiply z, and they're summed up. So there's nothing to prefer x over y, or nothing to distinguish x over y in the way they appear. So they're, the first derivatives should be similarly symmetric as well. Okay. Now you can also get these derivatives by using the quotient rule directly on this explicit definition of function z as well. So for instance, your dz dx. So you need to remember your quotient rule. So you have the square of the denominator function. 0 to b, and then the top, then you have the denominator function multiplied by the derivative of the numerator one, the derivative with respect to x. So this would just be minus y. Then you've got the negative of the numerator, 1 minus xy, multiplied by the derivative of the denominator, which would just be 1. So you've got another factor 1 there. I won't bother writing that down. So that seems to be what you get. That x plus y all squared. To minus xy minus y squared minus 1 plus xy. Which, so the xy's cancel, so you just got minus y squared minus 1 over x plus y all squared. Yeah, but you may have a bit of figuring out to do to reconcile this expression here with this one over here, making the substitution of z and seeing that they don't come. Okay, but any questions or queries? Okay, I think I'll leave it there for the moment. So for the tutorials this week, we've got all of exercises 1.1 we could be working with. We'll have a look at Stephen's linear algebra as well.